Okay, so we're going to start. So I uploaded some. I think Alberto uploaded some pictures for me. They are essentially the other blackboards in which I made a quick summary of what we did 2 weeks ago. So if you have them with you, essentially what we did is that we have the context of a complex semi-simple Lie algebra G, of which we took a maximal toral subalgebra. Associated to this, we have a system of roots, which we call delta, and this system of roots induces a root space decomposition of common eigenspaces. In the, in the toral subalgebra T, we took the elements with real components, which we call T of R, and we said that this is a real form of T. The killing form induces a non-degenerate metric in the toral subalgebra T, and when we restrict to the real form, we have a Euclidean dot product. So this allows us to identify the toral subalgebra with its dual via the Riesz representation theorem, and the same is true for the real form. So we define some vectors U alpha and H alpha, where U alpha is associated via the isomorphism, and H alpha is like a normalized version. And on the other hand, we have these SL2 systems, which we define by these E alpha, F alpha, and H alpha, which allowed us to see the semi-simple Lie algebra as the as the construction made from copies of SL2C. And the last thing we defined was the Weil group generated by reflections over the kernels on the elements of the root system. Okay? So this is where we stopped with the definition of the Weil group, and now I'm going to talk about Weil chambers. From this we're going to define a notion of positivity in roots. This will allow us to define simple roots, and we will see how this characterizes these semi-simple Lie algebras. So we start by defining regular elements of the of T of R. So let H be an element of T of R. We say that H is regular if alpha of H is never equal to 0 for every root H, for every root alpha. Okay? So we will call T of R sub reg by this will be the set of regular elements. And it is more or less clear that T of R reg is an open and dense subset of the vector space T of R. So why is this? This is simply because the condition alpha of H is equal to 0 determines a hyperplane in the Euclidean space T of R. So the complement is dense, and basically the set of regular elements is an intersection of a finite the intersection of a finite family of open and dense subsets. Okay? So T of R reg is open and dense in T of R. Okay? And from this we will define Weil chambers to be the connected components of this open set. A Weil chamber is a connected component of T of R. So later on we will see some examples of these subsets and these Weil chambers. And now we start with Thomas's favorite thing, which are facts. So the first fact is that the Weil group clearly it acts on the Weil chambers, it permutes the connected components, and it turns out that the action is simply transitive. the Weil group acts simply, transitively on the set of regular chambers, on the set of Weil chambers. So what does this mean? Essentially that given two Weil chambers C and D, there exists a transformation which carries C to D and it is unique. There is a unique transformation such that theta of C is equal to D. So this is the same as saying that the action is transitive and free. Okay? So next fact is that if we take the group of all interior automorphisms that preserve T, okay, so we take N to be this group, and we're going to take T to be the connected subgroup of the set of interior automorphisms of G with the algebra as T, then the Weil group is the quotient. If I remember. Yes. Then we can give a new description of the Weil group using these two subgroups. Essentially, the homomorphism which takes an element of N to its restriction to T of R, which is in the Weil group, is surjective. We mentioned that on the in the earlier session, and its kernel turns out to be T. So from the first isomorphism theorem, the Weil group is going to be isomorphic to N mod T. Okay? And from here, we're going to define some a notion of positivity in the roots by fixing now a Weil chamber. So remember that we have fixed a maximal torus of algebra, and now we're going to fix another component. So let's fix a Weil chamber. Which we call D. Okay? So D is a connected set in which every root is non-vanishing. So the root is going to be either always positive in D or always negative in D. So if alpha is a root, then either alpha is positive, no, I'm going to write it, either alpha is positive for all h in D, or it's negative. So we're going to say precisely that alpha is positive if this is the case, and negative if this is the case. We say, respectively, that alpha is positive or negative. So different elections of the Weil chamber are going to give us different possibilities for the positivity in the root system. And we're going to just define delta plus to be the set of all positive roots, which we denote by a natural choice of using the more than sign, and delta minus to be the set of all negative roots. Okay? And furthermore, we're going to define the simple roots to be all positive roots which cannot be written as combination of other positive roots. So, an element of delta plus is simple if it cannot be written as a sum of positive roots. And we define capital pi to be the set of all simple roots. And since it's a finite set, because roots are finite, I'm just going to give an enumeration, alpha 1 up to alpha n. Yes?
When you define a wave chamber, when you really only need one element in the wave chamber.
So this is that's another option. So you could use just one element, one regular element, but the thing is that if you take two regular elements in the same Weyl chamber, the notion of positivity is the same. So,
Yes.
and I believe that different Weyl chambers give always different notions of positivity. So that's why we use Weyl chambers to have so as to not have different criteria that in reality give the same positive roots.
When you say wave chambers, you want to fix a point. You only
Yes.
need a point in the wave chamber.
Yes, in practical effects, that's true. You only need one. That's no problem. This isn't the only way to define positive roots. So there are more ways, and I think there are references in which they only use one regular element instead of the whole Weyl chamber. They're the same thing, but yes. In practical effects, you only consider one element. So the thing is that the choice.
Sorry, the thing is that if you choose a root inside a specific Weyl chamber, it doesn't matter which, a root, an element in a Weyl chamber, the criteria of positivity will remain the same, independently of your choice inside the Weyl chamber.
But if you change the chambers, now it's different. It's like when you see that a non-vanishing continuous function is positive. You just test it at one point and it's enough. So this set of simple roots is a basis for the dual space. And yes.
If you do this construction in the conversely, I mean, if you pick a point and you don't know which is the wave chamber that regular point belongs.
Oh. We are having some technical difficulties.
I want to know the converse.
Yes.
Construction. You take a regular point, then you can know in which wave chamber you are.
Yes, because it's a connected component. It's unique.
Okay. No, I mean looking the roots, evaluating the roots in the regular element, you know which is the wave chamber you are. Isn't it?
Just by knowing the signs of the roots, you mean?
Yes, you know the
Yes.
sign of the roots. So
Yes, you know it. But you can just think as the connected component of the set of all regular elements containing the point. So first, it's a basis, but more importantly, roots are going to be written as integer combinations of simple roots. Any element, any positive root is of the form alpha I1 plus alpha IK. Okay? It's a sum of simple roots. Integer combination. Also, the set of simple roots is a basis of the dual space. Which means that since the dimension of this real form is equal to the dimension of the torals of algebra, then the set of simple roots has the same cardinality as the dimension of T, right? Which is equal to the rank of G. Which, to be honest, I don't remember how we wrote it. Okay? Any element of the root system can be written as an integer combination of the simple roots, where, as I said, the ki are integers, but either all of them are greater or equal to 0, or all of them are less or equal to 0, where all ki are non-negative, which is the case of positive roots, or all ki are less or equal to 0 in the case of a negative root. We usually say that pi is called a base. Not basis, base. No, I can still write here. Listen so much. More on this. The Weyl group, now thought of as transformations in the dual space, which we wrote as W super V, acts simply, transitively, on the subsets of positive roots. By subsets of positive roots, I don't mean any subset of the set of all positive roots, but all the subsets that can be regarded via sum of the Weyl chamber as the set of all positive roots. I think it's a little ambiguous how I phrase it here, but I don't really know of a better way to say it. And as well as the subsets of simple roots. Subsets of simple roots. More than that, given any root, we can always assume that it's simple. We can find a Weyl chamber of which alpha is a simple root. And finally, remember that the Weyl group was generated by all reflections over the kernels of all roots, but in reality we can take only the simple roots in the set of generators. The Weyl group is generated by all the reflections on the hyperplanes associated to simple roots.
Can anyone hear me?
Okay, and now we define a special element in the dual, which is going to be the 1/2 of the sum of all positive roots. So fix a Weyl chamber and we define this special covector gamma to be the sum of all positive roots associated to the Weyl chamber divided by 2. Oh.
Yeah, sorry. So I'm there.
Can anyone hear me now?
So,
Can anyone hear me now? Hello? 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 Tell me if you can hear me. Hello? I can't hear you now. Hmm. I can't hear anything. I think the audio is lost. Hmm. Sorry, guys. This must have been it.
you're muted.
Oh yeah, now I can hear you.
Vale, agora mutea.
Oh no.
So
Can anyone hear me
answer your
now?
question now. I think we can hear you.
Oh, the audio is lost again.
Dare voz a Juan.
Yeah, so let's try now if you can hear the question.
Can anyone hear me now? Oh yeah. So apparently you can, but you have to mute yourself in order for there to not be an echo. I can maybe ask the question, and then I mute myself so that you can reply, and so you'll be muted during the question. I think that's the best option, right? Can you nod your head? If you, oh yeah, cool. My question was that if I get it right, the statement on the right was that any root can be made a simple root by proper choice of positive roots, by proper choice of election. I think this is only true if you assume that your root system is like reduced. Or are you? I mean, yeah, sorry. My point was that, like, yeah, it's not true for an arbitrary root system, right? I was just going to remark that, like, if in the complex case everything is reduced, so I think everything should be true. But like, if you go to an arbitrary root system, or for example to a real semi-simple case where you can have the root system BCR, then this is no longer true, right? This is just the point to clarify. Sorry.
So in the real case, I'm not familiar with how this must happen, but we are in the complex case, and so in theory the statement is true. This is exactly as Onishchik says. So either I read something wrong, or I think the result is correct. So in the complex case, every root can be regarded as a simple root once we choose an adequate Weil chamber, but we can look for this in later on. Later I'll check if this was right, and if it isn't, I'll put a message on the group.
Okay, great, thank you.
But thanks. Okay. But yeah, the real case will go after.
Just a little comment. Maybe it fails when you deal with these BC root systems, right? That's where problems could appear.
Yeah, it does, because the root which is double of another root cannot be simple.
I'm not sure because I read it quite long ago, but I think it is true in the real case. Is if you ask for the root, if you consider the roots such that half of the root is not a root, so ones where they are basically not the double.
Yeah, okay, great. That sounds sensible.
Yeah. Okay, so not if the system is reduced, but if the roots, the roots are reduced roots.
Yeah, it's clear. Thanks.
I'm not sure. I think that's on labs.
Okay.
But I wouldn't say it for sure.
Yeah.
Great, thank you.
Yeah. So let's continue. And please, Ivan, I think it's better next time if you wrote your question in the chat,
Or you can ask it. I can hear it.
or you can just ask it, and Tomas will repeat it. Okay.
Okay, great.
Okay.
Yes.
Perfect. So I define this new root to be the same, well, this new covector to be the sum of all positive roots, and I divided it by 2. And so first, it turns out that the reflections on simple roots are going to preserve positive roots. So what we have is that given a positive root and a simple root, then if we reflect by the hyperplane determined by beta, so this is going to be a positive root, except when alpha is not equal to beta. So if alpha isn't equal to beta, this new element is also a positive root. If alpha is equal to beta, so what we have is that the reflection is equal to multiplying by -1. It's just an orthogonal reflection. So in particular, if we apply this to our new covector gamma, the reflection is going to give gamma minus beta, okay? And also, gamma of h beta is going to be equal to 1 for every simple root in pi. I think I wrote this wrong. Gamma of h beta is equal to 1. Okay, so we're coming closer and closer to Cartan matrices and the Dynkin diagrams. So remember that we were able to give some sort of decomposition of the semi-simple D algebra into SL2 systems by choosing these vectors H alpha, E alpha, and F alpha, and now we're going to resort to them again, just to make the notation a little simpler. Remember that we have these simple roots indexed. So the set of simple roots was alpha 1 up to alpha L. So we're going to define H to be Hi to be H alpha I, Ei to be E alpha I, and Fi to be F alpha I. So remember that we constructed these vectors in order to make SL2 systems in G. And we define A sub ij to be alpha I over Hj, which is equal to 2 times the scalar product of alpha I and alpha j over the norm squared of alpha j. Okay, so this determines an L by L matrix, which we call the Cartan matrix. So this is called the Cartan matrix. Okay, and this allows us to now review the the relationships between these HIs, EIs, and FIs in terms of these new coefficients A sub ij. To be more precise, the set of all HI, EI, and FI is a set of generators of the Lie algebra. Generators in the sense of Lie algebra, not in the sense of a vector space. It's a set of generators of G that satisfies the following properties. So the following bracket relations. Hi bracket Hj is simply 0 because both vectors are in the total subalgebra. Okay? Hi bracket Ej is equal to Aj Ej. This is because of the definition of the Ei. What? No, it's a no. There is no sum here. Aj times Ej. Look that the indices are here. I'm not summing anything. So if I'm going to sum anything, I will use the sigma notation. There aren't going to be any complex sums here. And Hi times Fj is equal to minus Aj Fj. Remember that Ei times Fi was equal to Hi by the original construction. And finally, Ei times Fj is equal to 0 whenever I and j are different indices. So this set of generators is what we're going to call the canonical system of generators. Okay? Do you see anything weird?
Because they are choosing on a specific basis like this. Okay, now I
Yes.
understand everything. Okay,
Yeah, so
Okay.
if you want, I can recall what this was.
No.
So it was in the picture.
So one question is, maybe they cannot hear me. Can you relate EI and FI by complex multiplication here?
By complex multiplication, yeah, they should be scalar. No,
Is one of them I times the other?
no, because we define them so that Fi, so that Ei was in G alpha I and Fi was in G minus alpha I. This was the construction.
Okay.
This was the construction. So no, they are not multiples of one another.
Okay, I thought they were living in the same root space. Okay.
No, the Fi are associated to negative roots, while the Ei are associated to positive roots.
Okay, and then I don't like the notation. I think it's really confusing.
Yeah, it's the one we
Maybe
have.
it should be minus alpha I or something like that. But
Yeah,
anyway.
but I think Onishchik uses this notation to emphasize that we are working with things that look like SL2C.
Okay.
But now we're going to blame him. We're going to blame him and say that we're just stuck with this notation. So this gets, as I said, this receives a name. The name is the canonical system of generators. And again, they're generators in the Lie algebra sense. So Hi, Ei, Fi is the canonical system of generators. And remember that the choice depended on the torals of algebra and the set of simple roots associated to the torals of algebra and the set of simple roots. Okay, so we define this Cartan matrix for a complex semisimple Lie algebra, and this turns out to be some sort of invariant in the sense that if two Cartan matrices are the same, they determine the same semisimple Lie algebra. I'm going to be more precise with another fact, which says that given two complex semisimple Lie algebras, and we make the choices of maximal torals of algebras, we make choices for Weil chambers respectively. So this gives us two canonical systems of generators, one for each Lie algebra, with canonical systems Hi, Ei, Fi, and Hi bar, Ei bar, and Fi bar. So these two determine two Cartan matrices. So if they're the same, then G is equal to G bar. If A is equal to A bar, then there is a unique isomorphism phi from G to G bar such that I'm going to put here that it's an isomorphism phi of Hi is equal to Hi bar, phi of Ei is equal to EI bar, and phi of Fi is equal to Fi bar. So I haven't looked up the proof, but I think it's just because the relations are here, and the fact that the Cartan matrices are the same means that the relations on this instant of generators are the same. So maybe it's direct, but I don't want to put myself on the line. At the very least, it seems reasonable enough. Okay. So this information allows us to recover the Lie algebra. Everything all right?
Yeah, it makes perfect sense.
I mean, I think the proof is, I think it should be easy to prove. Just a thought. Another way to compile the information on our semi-simple Lie algebra is going to be via the Dinken diagrams. So we're going to have some sort of equivalence between complex semi-simple Lie algebras, Cartan matrices, and Dinken diagrams. And I think it's worth noting, even though you all know this, Cartan matrices are classified. And the same is true for Dinken diagrams. I think that the classification for Dinken diagrams is at the end of the book. I don't know of the classification of Cartan matrices, if it's there or not. In the end of the book, I think there's the classification of all Dinken diagrams.
Do they classify Dinken diagrams or Santana diagrams?
I think they have the table for both.
Yeah.
They have the table, but they don't derive the classification of. Yeah, but I mean, this is an introductory chapter. I don't think they derived anything of this. We can? Okay. So, Dinken diagrams. So as I said, we're going to to collect the information of the semi-simple Lie algebra in another form. Okay? So we have a complex semi-simple Lie algebra with its associated torals of algebra, which we chose, and a Weil chamber, I don't know, G. So from this, we get a Cartan matrix. Okay? So first I'm going to say some properties about the Cartan matrix. First is that the coefficients aij are integers, and when I isn't equal to j, they are either 0, -1, -2, or -3. And as a consequence, the number mij, which is equal to the product of aij times aji, is going to be either 0, 1, 2, or 3, whenever I isn't equal to j. Also, we also know what values the angle between the roots can take. So the angle between alpha I and alpha j, remember that these were the simple roots. I'm denoting the angle by the symbol, which we call theta ij, is equal to lowercase pi times 1 minus 1 over some number n sub ij, where nij is either 2, 3, 4, or 6. Okay? And this is respectively, with respect to this, if I remember correctly. Okay, and finally, the quotient of the norm of alpha j and the norm of alpha I is equal to mij if mij isn't 0 and this quotient is greater than or equal to 1. Okay. Anything? Do you see anything strange?
So, can you derive more that expression? I times, what is the outcome of that?
What's the
result of doing that? I
of what?
of that. Can you simplify it a bit more?
Yeah,
Which are the angles then?
Yeah, so they would be pi over 2, 2 pi over 3, 3 pi over 4, and 5 pi over 6, no?
This is strange, right? Because I think when you multiply two simple roots, the inner product is negative. So the angles are not.
Maybe it's because the angle is not oriented.
What I'm saying is that you don't have these angles in the first column. The angle, I think, is not there. I think all these angles are greater than pi over 2.
Yeah, I see what you mean.
I think I'm totally right.
Yeah, I don't doubt you. I don't doubt you, but I don't know if anyone has the reference here.
The construction of the angle comes from the Spark.
The Schwarz inequality, yes. Yes, and from the fact that
you only can define the cosine of the angle. You can define
yeah.
the sine of the angle. So, I mean, I think the point you can orientate the angle because you only can define the cosine.
Yeah, I think the angle is unoriented, so it can only take values between 0 and pi. So we can't have 3 pi over 2 as an angle, really.
When you look at the draw of roots
Yeah, it's a picture of the
R2,
roots.
I think that if you consider simple roots, that they don't make acute angles.
But here,
I don't know if you remember something different.
But here the smallest angle is a 90-degree angle. The smallest angle you can make here is pi over 2, which is a right angle.
Yeah, but I think that they all are greater than pi over 2.
They are all greater than pi over 2.
So the algebra is simple. No, there's root systems. A1 plus A1.
Pi over 2, exactly pi over 2. But they have to be pi over 2 or greater than pi over 2.
Yeah, and that's the case. Pi over 2, 2 pi over 3, 5, 4, yeah. Pi over 2, 2 pi over 3, 3 pi over 4, and 5 pi over 6.
Okay, it was my mistake, my fault. Everything works perfect. It was me that I don't remember how to add fractions. Okay, it's perfect. Yeah.
But you say it like the rest of us know how to sum fractions. So, without further ado, I'm going to describe the algorithm in order to to make a thinking diagram. So the thinking diagram is a graph, and the nodes are going to be the simple roots. Okay. And then I'm going to say which are the edges that we're going to consider. The edges are going to have multiplicity in the sense that we can have more than one edge connecting two nodes. So we define a graph. Which is called the thinking diagram as follows. First, given, take a vertex for each simple root. So there are going to be as many vertices as the rank of the semi-simple Lie algebra. 2. Given I and j, we join alpha I and alpha j with an unoriented edge of multiplicity ij. Okay, so remember that this was the product of aij and aji. So there are going to be either no edges, 1, 2, or 3. And finally, if the norm of alpha j is greater than the norm of alpha I, we orient the edge with an arrow from alpha j to alpha I. Alpha I, yes. So I'm identifying the simple roots with the nodes. So it would be something, I'll write something like this. And so this information is exactly the same that the one we have in the Cartan matrix. So as a consequence, the diagrams determine the Lie algebra up to isomorphism. Thinking diagrams determine G up to isomorphism. Okay, so I'm going to make a small remark about direct sums. And from here, either I can go on with representations, or we can go directly to some examples of semi-simple Lie algebras where we compute everything. So as you prefer.
Maybe examples and then we will let representations
for the next day. So the examples are not going to be. I'm not going to go through the examples because, to be honest, I solved everything using Mathematica. Trying to do this by hand is pretty much torture. So just a comment on direct sums. What happens?
Tomax likes to do this competition.
I like to keep my hand. So
I think I like to write matrices.
so let's.
For arbitrary.
So let GI be the matrix, be two some complex semi-simple Lie algebras. So we have two, and we take the direct sum. So it turns out that the toral maximal subalgebras are obtained by taking a maximal toral here and a maximal toral here. So it decomposes. They decompose. Maximal toral subalgebras are of the form T1 plus T2, where each Ti is a maximal toral subalgebra. Of each G. Yeah, so
Então, agora, quítate o micro.
sí,
E date voz.
yo tengo voz.
¿Sabes?
Supuestamente sí. Bueno, el micro.
Claro.
Lo que no sé es a qué está conectado el micro.
¿Estás sonando?
Sí.
Vale.
So you can hear me, no? Yes. Okay. So let's go on. So it's direct because we are trying a dimension or and whatnot. We do all of this. It's the sum of the duals. So let's call this T, and the dual of T is the dual of T1 plus the dual of T2, and this means that the system of roots is going to be the union of the roots associated to each of the maximal products of algebras. Also, the same equality that we have here is true in real forms. More. Yeah. Finite chambers are products of finite chambers. Are of the form V1 times V2. So the set of simple roots is going to be the union of the sets of simple roots associated to HGI, where these two sets are orthogonal. And to finish, from this, we deduce that this breaks the thinking diagram into non-connected parts, and it can be shown that G is simple if and only if the linking diagram is connected. Okay. And more generally, remember that we had a decomposition of this semisimple algebra into simple ideals. Well, this corresponds to the connected components. Simple ideals are the same as the connected components of the linking diagram. And with this I finish this part of the encompassing simple algebras. So originally I had two examples of SL3C and SL3C. So SL3C is another way of writing SL2C, so I'm going to just skip directly to the more non-trivial example. So this was the first example. Okay. So, example. So the example is going to be the semi-simple algebra SL3C of all matrices of trace 0. Okay? So, here we can choose the maximal total subalgebra to be the set of all diagonal matrices. So this can be shown to be maximal total because matrices that commute with diagonal matrices are diagonal. So which is the rank? The dimension is 2. Now I'm going to just determine the roots. So I'm going to define some linear forms which are going to be taking each component of the diagonal matrix, which we call EI. Let EI of H to be Ci. Okay, we take the ith diagonal element. So it's an element of the dual space. Well, we're going to define alpha 1 to be E1 minus E2 and alpha 2 to be E2 minus E3. So we are subtracting consecutive diagonal entries. The set of all roots is going to be alpha 1, alpha 2, alpha 1 plus alpha 2, minus alpha 1, minus alpha 2, minus alpha 1, minus alpha 2. So, for example, this illustrates how the root system is closed under multiplying by -1. And who are the associated root spaces? There are 6. So G alpha 1 is a straight line generated by E1, 2. Here, Eij is the matrix that has every entry 0 except for the ij component. So the standard, kind of standard matrix. G alpha 2 is equal to E3. G alpha 1 plus alpha 2 is C times E1, 3. And G minus alpha 1 is equal to C into 1. G minus alpha 2 is equal to C times E 2. Finally, G minus alpha 1 minus alpha 2 is C times E 3. So the root space decomposition asserts that, yeah. Okay, there's a 0 at the end. Yes. Yeah. So the root space decomposition asserts that the algebra is the direct sum of diagonal matrices and all of these straight lines. Okay. So in this case, which is the real form T of R? Can anyone say who is T of R? So here we have complex matrices, the real part, the real part, exactly. So that's x, y, and z are real numbers adding up to 0. Okay. The killing form can be shown to be 6 times the trace of xy. In general, it's 2n times the trace of xy. And here I'm going to write all the matrices associated to the roots. So first, u alpha 1 is equal to 1, 6 minus 1, 6, 0. U alpha 2 is given by 0, 1, 6, and 1, 6. And u alpha 1 plus alpha 2 is equal to 1, 6, 0, and 1, 6. U minus alpha 1 is equal to 1.6 and 6, 0. Remember that it's that taking alpha into U alpha is linear, so we're just going to multiply everything by -1 here, and this is the sum of these two. Linearity. 6, 6, and U minus alpha 1 minus alpha 2 is equal to -1/6, 0, and 1/6. And apart from this, we have these H alphas, which are going to be basically multiplying everything by 6. Okay? Because the norm of all the roots, if I remember correctly here, is 1/3, or 1 over the square root of 6. So essentially we multiply everything by 6 and we get the H alphas. Every H alpha is equal to 6 U alpha here. So it would be 1 minus 1, 0, 0, 1 minus 1, and so on. And finally, I'm going to write how the root system looks and divide chambers. Okay. Well, I have something more. So once you compute the angles between the roots, it more or less takes this form. Yes, this is the origin. Alpha 1, this is alpha 2. The angle between alpha 1 and alpha 2 here is 2 pi thirds. Okay? So here the angle is pi over 3, and here is 2 pi over 3. And we have their negative counterparts. Okay, so this is how the root system looks. And divided chambers, let's see if I draw this correctly. By taking also one complement, the hyperplanes are going to look something like this. Hopefully I write this properly.
Maybe you should.
Yeah,
Draw the vectors the same.
yeah, the lengths are terrible, but they are of the same length.
Yeah, not twice.
This is
as
not
long.
So in reality, the vectors are isometric. In this drawing, they are just homeomorphic. So the hyperplanes, if I go to this is P alpha 2. This is P alpha 1. And this is P alpha 3. P alpha 1 plus alpha 2. And what is the set of regular elements? Everything else. So again, it's more or less clear that the set of regular elements is open and dense because its complement is just a union of straight lines. For example, we can choose this to be a right chamber. When we take to these right chambers precisely a set of all elements such that alpha 1 of h is equal to 0 and alpha 2 of h is equal to greater than 0.
So I was making fun of your drawing technique.
I mean, you get the picture, even though it's
Yeah. Okay. Anyway.
So, yeah. So these chambers forces alpha 1 and alpha 2 to be positive, and here delta plus is alpha 1. the positive and negative roots. And it's more or less clear that the simple roots are alpha 1 and alpha 2. Again, being this in accordance to the rank being 2. So finally, I'm going to be the system of generators and the matrix and the different diagram. So the H1 is going to be 1 minus 1, 0. The E1 is going to be pretty much the E1, 2. F1 is 0, 0, 0, 1, 0, 0, 0, 0, 0. H2 is 0, 1, 0, 1 minus 1. H2 is 0, 0, 0, 0, 0, 1, 0, 0, 0. And F2 is 0, 0, 0, 0, 0, 0, 0, 1, 0. A lot of binary code here. Finally, this is just too beautiful to erase. The Cartan matrix is 2 and 1. And the linking diagram is given by just one vertex joining alpha 1 and beta. So this, either the matrix or this linking diagram determines SL3C unity. And this is all that I wanted to talk to you about in this lecture.